Let us discuss about the special function registers in the datasheet. Right. We had the discussion about this in the last session. Right. From here we'll proceed. The special function registers are actually these special function registers are part of RAM, on-chip RAM. Right now, the special function registers are registers used by the CPU and peripheral module for controlling the desired operation of the device. These registers are implemented as static RAM, a type of RAM, SRAM. A list of these registers are given in table 2.1. Actually, these registers are divided into different banks. Totally, we have 4 banks. Bank 0 to bank 3. Bank 0 to bank 3, I believe. Totally 4 banks. Each bank has their own number of registers associated. Right. Special function registers can be classified into 2 sets: core CPUs and peripheral. So CPU registers and peripheral registers. These are the 2 categories. The CPU registers may be your page pointer and then program counter, a working register. Those can be the core CPU register. The peripheral registers are registers used to control the one second. I mean, right. Those registers are used to control peripherals like timers, serial port interface, like that. Right? Those registers associated with the core functions are described in the detail in this section. Those related to the operation of peripheral features are described in detail in the peripheral feature section. Right? So they have separated them into 2. These were core functions. Right. So here we have indirect function register, INDF. So what is the use of this register? When you point, there are certain RAM location, those doesn't have a name associated with it. For example, we have a register called status. The status is also having an address in a memory address. Here 3 is the address for status, but there are certain memory location, those doesn't have any associated symbol with them. Symbol means name with them. To access them, we can use this INDF. You can load the indirect to this particular register. You can load the address of the memory location that doesn't have any name. For example, let's say some 200, something like that. Then you can use this this register to navigate different memory location. Actually, this is a pointer. INDF is like a pointer variable. What is the property of pointer variable that we studied in the past? Pointer is a variable which holds address of another variable. Right now, then when we use pointer plus plus, it makes a jump based on the size of our data, size of the data type. It will make a jump every time. When we increment, it will move that much level. Like if it is a character pointer, it will increment every time 1 byte per increment. If it is an integer, 4 bytes per increment. If it is double or float, 8 byte per increment. Like that, they will make the increment right now. So like that, we have a pointer, which is actually indirect function register, they used to call that. Addressing this location uses the content of FSR, file system registers, to address the data memory, not the physical register. So these were not named memory locations. These were the locations. Those are doesn't have any name associated with them. Right? To access them, we will store the address of that one to this particular register and will access it. Right now. Then timer NAT, it has the address 1 in bank NAT. So this timer NAT will have, I think it is 1 byte in size. You can load the timer's period in this particular timer NAT register, right? timer module register. That is what they say, that one. Then PCL, program counter. The program counter is having 2 bytes. Why 2 bytes? Why don't we can do it in single byte itself? No. Why they are using 2 bytes? Any idea? So this PCL is program counter LSB, least significant bit of program counter right now. So program counter, as they said here, 2 bytes, PCL and PCH, totally how much? We are getting 8 plus another 8, 16 bits we are getting right now. Are they using all 16 bits? If that is the case, number of memory address that we can address in program memory will be more. But in this particular microcontrollers that we are discussing, it is having only 14-bit address, 14-bit program memory address. Right. If that is the case, how many bits are required?
Sorry, sir, can you repeat once again?
Actually, I told that program memory of PIC controllers that we are considering for the project has 14 bits.
Yes, sir.
If that is the case, to address the total number of memory location in the program memory is 2 power n minus 1.
Yes,
2
sir.
power n minus 1 means 2 power 14 minus 1.
Yes, sir. 2 power 13. Yes.
Right now, if that is the case, not 2 power 13, 2 power 14 minus 1. Total, actually, you have to
Okay.
find 2 power 14. In that one memory location, you have to reduce.
Yes, yes.
Got it now.
Yes.
So, if it is, we have only program counter of 8-bit means, that is 1 byte means maximum how much we can address? FF, 255 memory location only we can address. Yes or no?
Yes, sir.
So if that is the case, we need an additional 5 bits. Right, 8 plus 5, 14, right now. So the
13, sir. 8 plus 5.
8 plus 5, yeah, 13 bits, right?
Yes.
So here we consume 8 bits in the PCL, remaining 5 bits are here, PCL program counter. I think this is write buffer it is. PCLH will be there. This is PCL, no? So there will be a PCH. Let me tell you where it is. Write buffer for the upper 5 bits of program counter. I think this is the one, I believe. PCLH. Yeah. There is no PCH. PCL. Yeah, that's it. Every time we have program counter low only. Write buffer for the upper 5. This is the 5 bits. 5 plus 3, 8. No, correct only. Here they have remaining 5 bits. Totally, by combining PCL, PCLATH and plus PCL will give the complete address of the program memory. Do you understand what I mean to say? So in order to get to your 14-bit address, you have to, that means 14-bit address, you have to combine 13-bit address actually totally. So you have to combine PCL plus PCLATH. Both of them will give a complete address, program memory address that you are trying to access. And then there is a register called status. This is having the address. Actually, we are seeing the bank 1. Bank not is this one, right? So it is having address 3. See, 3 also status. Again, 2 also PCL. When it comes to next bank, there also we have PCL in 82 and status in 83. 2, 3, 82, 83. Then which is the address of the PCL? PCL, will they have a different copy in each bank? In bank 1, we have one physical register for program counter low. In bank not, they will have a one dedicated register to store program counter low. Is that the case? Or single program counter LSB will be maintained? The question is, do they mean a different memory location using 82 and 83, or it is the same location? See, here they say 82 also PCL, 83 also status, and then 2 also PCL, 2 also status. Then what is the address of PCL and status exact? Because it is memory location in RAM. If it is a memory location in RAM, it should be in one fixed location, no?
Yes, sir.
Right. If that is the case, why they are saying like this? PCL is 2, 3, 82, 83. Then which is the address of it? Physically, to store the program counter, there will be one location, but it is addressed via different address. 2, 82, for this status 383. When you try to access the data from 83, you will get what you have in data in 3. When you try to access data in 3, you will get what you store in memory location 83, which means that it is a physically one, but it has a different address. Right now, there are certain we have different services. Yeah, same person can have multiple credit cards. Right. That is possible, no? Possible or not? Possible. So it is something like that. The same thing has same physical register is having different memory location to address. That is what it is.